Okay, welcome to lesson 9 on electric potential energy. And so in this lesson, we're going to learn to use electric potential energy to analyze the motion of charges in an electric field. So with electric potential energy, we want to kind of recall what we learned about with potential and kinetic energy from Physics 151. So we'll recall that kinetic energy was the energy of motion, and potential energy was kind of a stored energy, or like with gravitational potential energy was energy due to position. Okay, and so if we had say a ball, and we picked the ball up and lifted it above the ground, and maybe the ground's down here, and so if we had the ball above the ground, and it was a certain distance above the ground, a position above the ground, a delta y we called it, then it would have a certain amount of potential energy. But if we were to change its position, maybe we put it lower down, then it was closer. It had less potential energy. It had the less potential to fall to the ground because of the gravitational fields. And we remember that gravity did work on the ball in that process, and we said that work and the change in potential energy were equivalent, but just the kind of in opposite directions, right? So if you do work, then you change the energy, and so if as long as the masses of the two objects were the same, then the only difference in potential energy or gravitational potential energy was the height at which it was above the ground. And then we also learned about a what we called conservation of energy, where we said that if there was a certain kinetic energy initially and a certain potential energy initially that a system had, then the sum of those energies it started with has to be the sum of the energies at the end of the interaction. And so we're going to apply this conservation of energy to electric potential energy. So we learned there's potential energy from due to position because of gravity. There was also potential energy. We learned about spring potential energy, based on the potential of a spring being compressed or stretched. And so we'll learn about another type of potential energy that is also can be conserved, this electric potential energy. So we'll recall that in an electric or in a parallel plate capacitor, the electric field pointed from the positive plate toward the negative plates. Okay, and the electric field, it'll do if we place a charge in between the plates. Well, then the electric field will do work on that charge. So say for instance we had we put a positive charge in here. Okay. The electric field is going to do work on that charge. Okay, because if we place a positive charge in here, what is it going to want to do? It's going to want to repel away from the positive plate and toward the negative plate. And so the electric fields will accelerate this charge toward the negative plate. Okay, and so remember that so it's doing work on it. Work has to do with a force over a certain displacement. And so what's the force that this charge is experiencing? Well, we learned this earlier, was that it was the charge times the electric field strength. Okay, and so the work done then, work is force times displacement. If the force here is charge times electric field, then the work is charge times electric field times displacement. And so we could picture this as being similar to a mass, or like a ball that is falling in the presence of a gravitational field. Okay, it's the positive charge is sort of falling toward that negative plate. Okay, and so the work done, right, we said the work done was equivalent to the change in potential energy. Okay, and we call this electric potential energy. So I'll just use a subscript for electric potential energy, and so if we could say the work done is the change. So if it had some initial potential energy to begin with, okay, and then it had some work done, well, then we could kind of make a general expression for how we can determine the electric potential energy of a charge. Okay, maybe it didn't have any potential energy to start with. Okay, if we were to put the positive charge right next to the negative plate, it's not going to have any potential, right? It's already come as close to the negative plate as it's going to get. So then, so then the only potential energy would be the work that is done then. So if we were to somehow move that charge away from the negative plate, then we would do work on it, and it would gain this amount of electric potential energy. Right? So the charge experiences a force, which means it accelerates. And so according to conservation of energy, then whatever potential the charge had here, what's going to happen to it as it accelerates? Acceleration means it's increasing its velocity. Okay, and so what do we remember about conservation of energy? Okay, if its potential energy decreases, well, then its kinetic energy has to increase. Okay, so there's this constant conversion from potential energy to kinetic energy. Okay, all right, so this would be the UI would be the initial, if it has an initial potential energy. And then the second part here would be the work that is done on the charge to give it some potential energy. So if we have a parallel plate capacitor set up like we do here, we have the positive plate down here, the negative plate up here, then we know the electric field lines are going to point up in the way we have it oriented here. And so if we have two positive charges, A and B, that are equal, can you tell which one will have more electric potential energy? Okay, so if it's just sitting there, if the charges are just placed there, then and we just want to consider from those positions which one has more energy, well, then what are we going to have to look at? Well, which one has more potential? Well, it's going to be A, isn't it? Because it's closer to the to the positive plate. Okay, so it has more potential to reach a higher speed when it reaches the negative plate. Whereas if we place it here at B, the same charge, then it doesn't have as much potential. So when it reaches the negative plate, it won't be going as fast. Right? Same as if we were to remember, if we think about this as something falling in a gravitational field. Well, the higher up you release it from, then the faster it's gonna hit the ground with. But if you just release it from a lower point above the ground and drop it, it's not gonna reach it with as much speed. So let's look at what happens to the energies as these charges move inside of a parallel plate capacitor. And so if we have a positive charge placed near a positive plate, we know that it's going to move toward the negative plate. And so this is equivalent to dropping an object or letting something roll down a hill. Okay? And so if the positive charge is moving toward the positive plate, or if instead it's moving toward the positive plate, so if we put it there instead and move it toward the positive plate, it goes in the opposite direction that the electric field points, then this would be like an object rolling up a hill or pushing an object up a hill. Okay, so the charge gains potential energy as it rolls up the hill or moves toward the positive plate, and it will lose kinetic energy. Okay, so if we were just to look at the charge moving toward the plate, then what's happening? Its potential energy is going down, and its kinetic energy is increasing. Okay? Whereas if it moves toward the positive plate, its potential energy is increasing, and its kinetic energy has to decrease. Okay? And then we see the opposite happen with a negative charge. Okay, so if we place a negative charge near the positive plate, like we have here, then it's not going to have a whole lot of potential energy, right? And so if we somehow push it to move toward the other plate, what's going to happen? Well, it's going to gain electric potential energy, but it's going to lose kinetic energy. And then if we place it near the negative plate, it's going to lose potential energy, but gain kinetic energy. All right, so here we have a positive charge, and I just drew like a little number line, so for reference here. And so if we place this charge here at the point 0, we know it's going to create an electric field around it, right? It's just going to point out radially in straight lines in all directions. Okay, if we then place another charge, okay, so let's call this charge Q1. If we take another charge and place it here at the position of 1, okay, what's going to happen? Well, we know that it's now in the presence of the field produced by charge 1. Let's call this one charge 2. And so the charge Q1's the charge Q1, it is creating this electric field that is essentially going to push charge 2 away. Okay? And the electric field, though, it's not uniform, right? So it pushes charge 2 away, but it's not uniform like in a parallel plate capacitor. Okay? Because remember that closer to the charge, the electric field is stronger, but further we get away, those field lines are further apart, so the electric field gets weaker. So it's not going to have a uniform force experienced by Q2 is not going to experience a uniform force, a constant force, like it would if we placed it in a parallel plate capacitor. Okay, so as it moves further away, the force is going to be decreasing. So if we wanted to know the work done on the charge by the electric fields, well, then we're going to have to do an integral. Okay, so we'd say what's the force of charge 1 on charge 2 over a certain distance, okay, from some initial distance to some final distance. Okay, and what do we know the force? The force is K times charge 1 times charge 2 over the distance between them squared. And we could pull some things out of the integral sign, right? The K is constant, Q1 is constant, Q2 is constant. Okay, and then the integral, then 1 over x squared is just minus 1 over x. And then we can evaluate that over x initial to x final. And then we'll find that the work done, okay, so final minus initial, so K Q1, Q2 over x final, minus the negative will be positive, K Q1, Q2 over x initial. Okay, and so we know that the change in electric potential energy, right, is the negative of the work done. Then the electric potential energy at any particular point is just going to be K Q1, Q2 over that the distance it is at that point. Okay, and then if energy is conserved, the work done, it's remember this from when we studied energy in 151, the work is independent of the path taken, right? So if you walked up a hill and zigzagged up a hike, right, you didn't count the total distance you walked, right, when you were figuring out your change in potential energy, gravitational potential energy. No, it was just from where you started to where you ended up. Okay, it was independent of the path taken. And so likewise, a charge, okay, if we take a charge and move it around, then and it zigzags all over the place and goes back, but then ends up at a certain point, then it doesn't matter. The total distance x is just from where it started to where it ended up. So if it started here at 1 and it zigzagged all over the place, back and forth, and you went over here and back, well, it's just that distance from 1 to 2. That's the only distance that is considered. All right, so let's try an example here. We have a proton is fired away at a 1 millimeter glass diameter glass sphere that has been charged to 100 plus 100 nanocoulombs. Okay, so let's say we have let's say this is the proton fired away with some initial velocity at a 1 millimeter diameter glass sphere. So sphere, let's put it over here. Okay, so we'll say this is the proton. This is the glass sphere. Okay, and so the proton's fired toward this glass sphere. It has a charge of plus 100 nanocoulombs. And we want to know what initial speed must the proton have to just reach the surface of the glass. Okay, so the proton's positively charged, the glass sphere is positively charged, so we can essentially model this scenario as if it were an interaction between two charged particles. But since the glass sphere is going to be far more massive than the proton, then we can essentially consider the glass sphere to be at rest, sort of like the difference between the mass of a ball that you drop and the Earth. And technically, there's some acceleration of the Earth, but it's so tiny. It's essentially nothing. Okay, and so that's the difference between even a glass sphere. It's very, it's a one millimeter. Okay, so really tiny, but it's still incredibly massive compared to the mass of a proton. And so we could sort of treat this as if the proton's sort of like a ball and the glass sphere is sort of like the Earth. Okay, the glass sphere is essentially at rest. Okay, and then we're given some also in some information about the proton is fired from far away. Okay, so if we're essentially very far away, then we could say that there's sort of not really any interaction to begin with. Okay, so there's really this clue here that it's from far away is really telling us that the initial potential energy is essentially zero. Okay, and so in order for the proton to just reach the sphere, then what's going to happen? It's going to have a certain speed initially, so that it's moving toward the positive bead, which it wants to repel. And so what's going to happen? It's going to shoot toward it, and then it's going to repel it. So we want to create a scenario where we give it just enough speed so that it just barely comes up next to the glass sphere. Okay? And so what does that mean? That means that the final velocity of the proton is going to have to be what? Once the proton gets here, it's going to instantaneously stop. Okay? And it's going to come to rest, and then it'll repel, it'll move back away. Okay, so let's look at our conservation of energy then. We have final kinetic energy, the sum of the final kinetic energy and the final potential energy has to equal the sum of the initial energies. We said the initial kinetic or potential energy was zero. And since the proton stops instantaneously when it comes near the sphere, then we could say that final speed is zero. That means the final kinetic energy is going to be zero. So basically, the final potential energy will have to equal the initial kinetic energy. So the electric potential energy is K times the charge of the proton the charge of the glass sphere over the distance between them equals 1/2 mass of the proton times its initial velocity squared. Okay, and so if we solve for the initial velocity of the proton, it's square root of k, the proton, charge of the glass over distance times the mass of the proton. Okay, so 2k are constants. Charge of a proton is a constant. You can look that up. The charge of the glass we're given is 100 nanocoulombs. Mass of a proton is a constant. We can look that up. What's x? Okay. Remember, x came from the final potential energy. Okay, so basically, what's its position? How far away are the two charges when they're finally near each other? Okay, well, you could say, well, it's kind of zero, right? Because they're right next to each other. But if we do zero, then we're saying the initial velocity is zero. So it's technically not zero. Okay, so really what it is then is that the size of the proton, how big is the proton compared to the glass sphere? We can't even see a proton. It's so small. Okay, right? We can't even see the atom with the most powerful microscopes. So we definitely can't see a proton. Well, we can see a glass sphere, right? Glass sphere is sort of like a grain of sand. It's hard to see, but you can see it. It's massive enough. It's big enough compared to the diameter of the proton. The diameter of a 1 millimeter glass sphere is very large. Okay, so really the distance here, if the proton comes right up next to the glass sphere, well, the distance would be the radius of the glass sphere. Okay, so the radius, the diameter is 1 millimeter, so the radius is 0.5 millimeter. Okay, this is sort of like when we measure the forces between planets, right? They're so massive we can't just say from the edge of the Earth, measure the distance from the edge of the Earth to the edge of the moon or something. No, because they're have such large diameter or radius, then we have to consider those as the distance between them too. We have to go from center to center, and you remember that from 151. So it's essentially the same thing here. So I will hopefully you will pause and do this, try to make sure that you get what I get. But I get 1.86 times 10 to the 7th meters per second. Okay, really fast. Okay. In fact, when we look at the speed of light later on in this course, which we symbolize with c, it's 3 times 10 to the 8th meters per second. Right, so now we're approaching a speed that we start saying is relativistic. Okay, it's when we things start moving near the speed of light, then we have to start considering relativity. So and so this is sort of where the laws of Newtonian mechanics break down inside the atom. Okay, and protons and other particles, they actually do travel near these speeds of light, and so we can't actually accurately describe and explain what's going on with this the basic mechanics that we've studied in 151, based on Newton's laws. So so that gets into a whole other realm, into modern physics and particle physics, which is very fascinating. But for now, we're just going to stick with the beginner's physics. Okay. So let's try one more problem here. And so this is, we have 3 charges now. And we want to know what's the potential energy in the group of these charges. So now, if we have more than 2 charges, well, the potential energy is simply just the sum of the potential energies of all the pairs of charges. Okay, so so we don't have to do vectors here, but we do have to do consider each pair of charges. So let's label them. Let's say this is Q1, this is Q2, this is Q3. Well, then the total electric potential energy due to this group of charges is going to be the potential energy between charge 1 and 2, plus the potential energy between charge 1 and 3, plus the potential energy between charge 2 and 3. Okay, so what does this look like? Well, it's K, the first pair, it's K Q1, Q2, over the distance between them. All right, for the electric potential energy between charge 1 and 3, it's K Q1, Q3, over the distance between them. And actually, all the distances are 3, so they could all just be the same. I could just call them OR if I want to. And then the final one is between charge 2 and charge 3. Oh my goodness. All right, so so one thing I see here is that I could kind of factor K out if I want to, right? And since all the distances are 3 centimeters, I could factor that out too if I want. And then what does that just make? Then I could just do Q1, Q2, plus Q1, Q3, plus Q2, Q3. Just a little extra step there, so we don't have to punch K in 9 times 10 to the 9th in 3 times, and we don't have to punch that in 3 times, so save a little bit of time there. Okay, so K over R, right, Q1 is 1 times 10 to the minus 9th coulombs. Q2 is minus 2 times 10 to the minus 9th. Q1 again is 1 times 10 to the minus 9th. Q3 minus 2 to the minus 9th. That's Q2 and Q3. 2 times 10 to the minus 9th times minus 2 times 10 to the minus 9th. Okay, and so what I see here first is I have 1 times minus 2, so that's going to be minus 2, right, times 10 to the minus 18 plus, let's see, that's going to be the same thing, right? Minus 2, so let's just do minus 2 times 10 to the minus 18th plus minus 2 times minus 2 is positive 4, so we'll add 4 times 10 to the minus 18th. And what do we see here? Minus 2 plus 4 is 0. Okay. So the potential energy of this group of charges is 0 joules. Okay. So all those, the amount of positive and negative charges there are and the amount of charge and the distance between them, they kind of all balance each other out. Okay, so now maybe if you were doing this, maybe you were glad that you didn't punch in K and R too, because it really, there was no point to it. We didn't even have to do it here because we saw that this sum in here was 0. Okay, so save a little time, save a little work. Okay, so here are the problems from homework 4 that you should now be able to get done. And there's one extra example problem on the Moodle page if you want some more practice with this. And so, did you learn to use the electric potential energy to analyze the motion of charges in an electric field? Okay, so we saw that electric potential energy, right, is the equivalent. We can have an initial energy, and there could also be the work done. So if there's any work done on the charge, and then we also saw that it was between two charges. It's K Q1 Q2 over R, and so we can also put it in terms of epsilon naught, which may be helpful in the future. Okay, so it's just how we determine the electric potential energy between two charges, and then we also saw what happens with protons and or positive and negative charges inside a parallel plate capacitor. Right? We know that the positive charge will want to move toward the negative charge, but if for some reason it had an initial velocity and we shot it toward the positive plate, well, we know that it's going to be losing some of that potential energy it started with, and it'll slow down. And then we see the same or opposite kind of thing actually happening with a negative charge in a parallel plate capacitor. Okay, then that's it for lesson 9.